Hello. Welcome again. Today we will be working with the simplex method in matrix form. If you want to do a quick review of matrix algebra, we invite you to watch a video called Operations with Matrices. Surely, this overview will help you to better understand this topic. The simplex method in matrix form is probably the most important version of the simplex method, since most of the software packages are based on this algorithm. Let us start formulating a problem, and then we will write it in matrix form. After we transform this problem into a system of equations, adding slack variables, surplus variables, and artificial variables, we will arrive to the following expression. Let us represent as x, the vector that present the names of the variables used in the problem. We will define as vector c, the coefficients of these variables in the objective function. We will define as matrix A, the matrix containing the coefficients of each of the variables in each one of the constraints. For instance, in third constraint the coefficient of x2 is 2. And this number is written in the second column of the third row of the A matrix. Finally, we will define vector B, as the vector that represent the numbers appearing on the right-hand side of the constraints. If you know the fundamentals of matrix algebra, you will realize that the problem can now be written as follows. Where x' and b' mean the transpose matrices of x and b, respectively. Let me rearrange the data on the board. The first step consists in finding a feasible basis for the problem. This implies finding the variables that will serve as basic variables. Since in this case we have three constraints, we must select three basic variables. The selected variables are the slack variables, S1 and S2, and the artificial variable, A3. With the columns of these variables found in matrix A, we form a new matrix. And we obtain the inverse of this matrix. Now, we must obtain the following matrices. You may not believe it, but the results of these multiplications represent the simplex method tables. To help us visualize the foregoing statement, let us recall the tables obtained in the tabular simplex method. This is the first table of tabular simplex method. Now, observe the result of the multiplication of the matrices. If you observe carefully, you will realize that the first matrix represents this section of the table. And the result of the second multiplication represents the right-hand column. As you can see, now we only need to compute the objective function row. To achieve this, we will create a row vector which will be called C sub b. The elements of this vector are the coefficients of the basic variables in the objective function. Recall that the basis consists of the variables S1, S2, and A3. The coefficient of S1 in the objective function is 0. The coefficient of S2 in the objective function is also 0. And the coefficient of A3 in the objective function is -m. Once we have this vector, we will multiply it by the matrices obtained in the previous step. And from the first of these results, we subtract the vector c. These last results correspond to the objective function in the simplex table. If all of the elements in this vector are positive or 0, we have finished. Otherwise, we go back to step 1 to select the new basis. The selection of the new basis is done as we have seen in the tabular and the algebraic simplex methods. we choose the smallest of the negative numbers in the objective function, and that will be the variable that enters the basis. In this case the smallest negative number belongs to the x2 column, and consequently x2 will enter the basis. To determine the variable that leaves the basis, we divide the numbers that appear on the right-hand side column by the positive numbers in the column of the variable that enters the basis, and we will choose the smallest of them. The smallest number corresponds to the A3 row, and therefore, this variable will leave the basis and hence, the new basis will be S1, S2 and X2. Allow me to erase everything from the board, and start with the Simplex method steps. As I was saying, the new basis will be formed by the variables S1, S2, and X2. With the columns of these variables in matrix A, we form a new matrix. The order of the columns is important. Now we obtain the inverse of this matrix and multiply B inverse times A and B inverse times B prime. We now obtain the vector of the cost coefficients of the basis, which is 0, 0, 4. Now, we multiply this vector by the two matrices obtained in the previous step. And from the first one, we subtract the C vector. Now let us compare these results with the table obtained in the second iteration of the tabular method. As you can observe, the methods are totally equivalent. Furthermore, I recommend you to identify each one of the operations with each one of the sections in the table, since this will be important when you study sensitivity analysis. Since we still have negative numbers in the last row we obtained, we select the smallest of them, and consequently, the variable x1 must enter the basis. When we divide the numbers on the right-hand side column by the numbers found in the x1 column, you will conclude that the variable that leaves the basis will be s1. And hence, the new basic variables will be x1, s2, and x2. Again, I will erase all the information to perform the next iteration. As we mentioned, the new basis will be formed by the variables x1, s2, and x2. Now we construct the B matrix. Recall that the order of the columns is important, and we obtain its inverse. Now we multiply B inverse by the A matrix and by the B prime matrix. We now obtain the vector with the cost coefficients of the basis, which will be 5, 0, 4. Recall that D coefficients are placed in the same order in which the B columns were placed. We multiply this vector by the matrices obtained in the previous step, and subtract vector C from the first of these vectors. If you observe the last result, you will realize there still exists a negative number in this vector. This means that we still need to perform at least one more iteration. The negative number corresponds to the column of variable S3, and therefore, this variable will enter the basis. We divide the elements of the right-hand side column by the numbers of the S3 column. Recall that if any of the numbers in the S3 column is negative or 0, it will mean that the entering variable can grow up to infinity. The results of the divisions are: the smallest of these numbers is located in the second position, and therefore, the variable that leaves the basis is S2. Our new basis will be formed by the variables x1, s3, and x2. Before proceeding to the next iteration, I invite you to compare these results with the ones obtained with the tabular simplex method. Once again, you can see that all the results are equivalent. I will erase all the information to start a new iteration. As we mentioned, the new basis will be formed by the variables x1, s3, and x2. We will create the B matrix, and compute its inverse. We multiply B inverse by the A matrix, and by the B prime vector. Now we obtain the vector with the coefficients of the basis and the objective function. And we will multiply it by the matrices obtained in the previous step. And from the first of these vectors, we subtract the vector c. As you can see, there are no more negative numbers left, and so, we have arrived to the optimal solution. The results can be seen in the right-hand column. The first of those values represent the value of the variable x1, the second is the value of s3, and the third one is the value of the variable x2. And the value of z is 74. These results also totally coincide with the results of the tabular simplex method. I hope you have understood that the simplex in matrix form is totally equivalent to the algebraic and tabular simplex methods. Even though the use of matrices can complicate the computations in this method, the fact is that if we use a computer, the results can be obtained quickly. And besides, this method will allow us to better explain the meaning of the sensitivity analysis. For this occasion, we have finished. I will see you soon.